In this video, we are going to go over the synthesis and recrystallization of adipic acid. So in Chem 261, we did a lab where we synthesized cyclohexene. And we synthesized cyclohexene from cyclohexane and catalytic acid. And the catalytic acid was either sulfuric acid or phosphoric acid, depending on what we had available. Now in this lab, we can use the cyclohexene from Chem 261 to now synthesize adipic acid. So this is the reaction that we're performing. We start again with cyclohexene, and then eventually we'll end up with adipic acid. So notice that we're going from an alkene, and now we're going to form something with carboxylic acid functional groups. And there's one on each side. So this is a ring opening reaction, and we're basically splitting that double bond in half and replacing each end with a carboxylic acid. Now there are a lot of reagents listed here above and below the arrow. So there's sodium tungstate dihydrate, hydrogen peroxide, potassium bisulfate, and something called a phase transfer catalyst, and it's given the name aliquot 336. And we'll talk a little bit more about this phase transfer catalyst in a bit. But the structure is shown down below. So we have a nitrogen atom in the middle, surrounded by 4 different alkyl groups. 3 of those groups are quite long, and then the other group is a methyl group. And then there's a chloride ion there to balance the charge on nitrogen. Now, this is a very green way to perform the reaction compared to previous methods or even current methods that are used. So let's look at the other methods that can be used to get the same product. So commercial preparation of adipic acid involves nitric acid, HNO3, but that is very hazardous to handle. Also, we end up producing dinitrogen monoxide as a byproduct, and that is a greenhouse gas. So if we can prevent the production of that gas, that would be better. Another way that we could perform this lab is by using potassium permanganate, KMnO4, and a base. Now, potassium permanganate does dye things purple, so it can get a little messy. But additionally, we end up forming this byproduct, manganese 4 oxide. So again, if we can prevent forming a byproduct, that is better ultimately because it's easier than just isolate adipic acid. So typically we would do this reaction in an undergraduate lab, but again, we're going to use these reagents here. So let's talk a little bit more about aliquot 336. What is the purpose of this aliquot? So aliquot 336 is called a phase transfer catalyst. So in order for our reaction to work, we need cyclohexene and sodium tungstate to mix. They need to combine forces. However, they are in different phases. So cyclohexene is in the organic phase, and tungstate, WO4, is in the aqueous phase. So we end up with 2 different layers in our sample. So how can we get these 2 to mix? Well, that's where the phase transfer catalyst comes in. So this chart is a little confusing at first, but let's just go over it really quickly. So at the top, we have our cyclohexene, And we're just showing through this arrow here that we're going to form adipic acid. But again, remember we said cyclohexene has to interact with the tungstate ion. But the tungstate ion is in a whole other phase. It's actually down here in this water phase. So this is our aqueous phase. Whereas up above is the organic phase. So in order to transfer the tungstate up to where we need it to be in the organic phase, we're going to use that phase transfer catalyst. So it's going to form a compound with the tungstate and pull it into the organic phase. Then the tungstate can interact with cyclohexene and form adipic acid. All right, now in that process, there's some other things that happen here. So the tungstate is eventually reduced, so it loses its oxygens. So that's what the red W here means. It means reduced tungstate. And eventually, the reduced tungstate will interact with sodium chloride and go back down into the aqueous phase. So now instead of WO4 bonded to sodium, we now have an ionic bond between sodium and our reduced tungstate. And then hydrogen peroxide can oxidize tungstate back into its original form. So this is just kind of a cool way of showing all of the different interactions that are occurring during this reaction. Now, you don't really have to know all the ins and outs of this reaction, but I just wanted to show you why we're using a phase transfer catalyst. It's to bring that tungstate out of the aqueous phase into the organic phase so that it can help cyclohexene turn into adipic acid. Now, additionally, we said that this is a catalyst. So at the end of the reaction, we saw that we can reproduce our catalyst by using sodium chloride there and hydrogen peroxide. All right, so just some notes on this reaction. The reaction is done under reflux, so you will want to review that section of the Zubrick lab manual. Cyclohexene is very volatile, so it can get stuck in the condenser, so in that middle part of the condenser. So halfway through the reflux, you'll want to rinse the walls of the condenser with water. You also want to be careful about the order of the addition of reagents. So you want to follow the procedure step by step. You also want to make sure that cyclohexene can't escape your system. So make sure to grease the joint between the round bottom flask and the condenser. Now, your procedure also asks you to use a sand bath, but we're going to use our thermo well. And make sure you're stirring the solution vigorously. We want to make sure that everything is mixed really well so that we can actually form adipic acid. Okay, so that is it for this pre-lab video. If you have any questions, please let me know.